Here we're going to look at question 15 from the BMAT 2019 paper. So in this question, we're simply asked which of the following statements about waves is correct, and then we're given 8 statements. So this might look a bit scary at first because we've got 8 different things to read, but we can go through them one at a time and try and work out an answer. Now, if you'd like to have a go at doing this yourself, then please just pause the video now, otherwise we'll have a go at doing it together. So, to start this question, let's just do exactly what I mentioned and go through the statements one at a time. So the first statement says that all longitudinal waves travel at the same speed. Now, if you don't immediately know the answer to this, you can just try and think about some examples and see if it stands up to that sort of test, see if that gives you some idea. And what we could do is consider some different types of longitudinal waves. And a nice easy one to consider is sound waves. And we can consider sound waves in air versus sound waves in ground. So this is something which you may have heard of before, but basically sounds can travel faster through ground than it is through air. And you can test this by, say, making a loud sound a very long distance away, say by dropping like something heavy against the ground, and by pressing your ear against the ground, you'll actually hear the sound before you hear it through the air. So this is going to immediately tell us that sound waves don't all travel at the same speed, or longitudinal waves don't all travel at the same speed, and therefore this first statement has to be false. Of course, you can think of some other examples, but this is just what came to mind, and I think it's quite a handy kind of intuitive way of thinking about it. Now, having said that, we can move on and look at statement B. So this statement says that longitudinal waves cause vibrations perpendicular to the direction of energy transfer. So if this is initially a little bit confusing, if you don't really know what it's asking, then we can go ahead and consider our little diagrams which might spring to mind when we think of longitudinal waves versus transverse waves. And they usually look something like this, which is that longitudinal waves travelling in this direction look something like this, going round like that. Transverse waves, on the other hand, end up travelling in this direction, but they end up waving up and down like this. So what that means is that the actual vibration in this transverse wave is moving perpendicular to the direction in which we're travelling, so at 90 degrees to, or like kind of at right angles to this direction that we're travelling in. Longitudinal waves, on the other hand, such as here's kind of like a sound wave coming from something over here. In this case, we can see that the waves will be moving in this direction. So the vibration, the waves are travelling parallel to the direction of energy transfer, the direction the sound is moving. So if we look back at our statement, which says that longitudinal waves cause vibrations perpendicular to the direction of energy transfer, we can see that this is actually transverse waves, so this is incorrect. Moving on, we can then go ahead and look at statement C, which just says that sound waves are transverse. We already know from thinking about our example in A that sound waves are longitudinal waves, that's why we use them. So this statement is also going to be false. The next statement, statement D, says that transverse waves are always faster than longitudinal waves. Now this statement might actually be quite tempting to go for, because the kind of classic examples of transverse waves are things like light and radiation. Whereas longitudinal waves, we might think of sound, and we know that light is faster than sound, so it might be tempting to go for this. But actually, there are a lot of different types of transverse waves and longitudinal waves. For example, we might think for longitudinal waves of the speed of sound in the earth through ground, which is quite fast. Whereas if you think of transverse waves, then some examples of this could be things like the ripples of water along the surface. The ripples like along the surface of some water, which can travel relatively slowly, or like the vibrations in a guitar ring, which might seem quite fast, but we wouldn't necessarily be completely sure are going to be much faster than sound is going to travel through ground. So hopefully this should raise kind of enough ambiguity that you think actually this can't necessarily be true. And we can conclude that D is also going to be false. Moving on then, we can look at statement E, which says that transverse waves are all electromagnetic. Well, we've just thought about some other examples. We said things like waves on a string, which just is going to immediately disprove statement E, so we know that's going to be false as well. Moving on, we can look at statement F, which says that ultrasonic waves are longitudinal. Now, ultrasonic waves are basically just really high-frequency sound waves. So, we know that sound waves are longitudinal. We've mentioned it loads of times before. So, yeah, this statement F is going to be the correct one. Ultrasonic waves are just sound waves which are longitudinal, or basically just sound waves. Now, just for the sake of completion in this answer video, we can go through the remaining 2 statements, which are that ultraviolet waves consist of compressions and rarefactions. Well, this might look a bit confusing first of all if you've not heard this word rarefactions before, but let's just think about what ultraviolet waves actually are. And we know that they're transverse waves, not longitudinal waves. Ultraviolet waves are just another form of light, which we know are transverse. So these are transverse waves. Now, compressions and rarefactions. Well, compressions doesn't necessarily sound right either. That sounds more like sound waves, which are kind of compressions through space and air. And that's exactly what this is talking to. Compressions are the points where we have our wave like compressed. We have a high density part in a wave. And rarefactions are just the opposite points, the points of kind of a lack of compression, if you like. So this statement is also going to be false. So now we can just look at our final statement, which is statement H, which says that X-rays cannot travel in a vacuum. Well, we know this is going to be false because X-rays travel from things like the sun. They can cause a lot of damage, but they're thankfully blocked by our atmosphere. But basically, X-rays are just, again, like ultraviolet waves, light. They are a kind of electromagnetic wave. And we know that they travel through a vacuum, so yes, we know that X-rays can travel in a vacuum, and that one's also false. So the correct statement then is just going to be statement F.